All right, welcome everybody. Welcome to another edition of CPSC 222. Before we start, any questions from last time?
I have a question about the textbook. Do we need the Zybook code from the bookstore, or will it be fine?
The one in the lecture in the syllabus should have the code, should have everything. It is a Zybooks generated just for this semester of this class. And I think the bookstore may or may not have the same one. I hope they do. Have any of you checked the bookstore to see if it's the same one? It is? Good.
You said the code is in the syllabus.
If the syllabus has a link, if you click on that, the code should be in the link.
It'll automatically apply to
We,
Well,
was this supposed to be free though?
I don't think it's supposed to be free.
Okay. Yeah, okay. I was just worried I missed out on the free.
No, it's not as free as far as that.
Right.
Oh, I don't know. He says, are you, the access code is what is automatically?
Yeah.
Yeah, when she goes there, she gets this.
It should be good. If you put small,
She followed the link. There's a link for access. Just leave it blank. Just leave it blank. Yeah. Your questions. Oh, you should get the book like yesterday. Okay. Your assignment might be tomorrow or next week. The TA is handling all the Zybooks assignments. There are a number of them, and they're, I think, 70% of your grade. So it's very important you get on that. Any questions, go to Caleb, TA.
What platform do you think will be informed about homework assignments? Will it be Discord or Blackboard or?
Everything is actually available in Zybooks. When you go to Zybooks, it will tell you what is assigned to you, what you have done, what you haven't. It's like its own little platform. I picked up my bike today, by the way. Thanks for fixing that. Does that make sense?
I added to the course a little too late for them later, and it's still close to me. I can't do the syllabus or anything on Blackboard. Is there any?
Okay, I can email you the syllabus.
Yes, that'd be great.
Okay, whoever doesn't have the syllabus yet, raise your hand. Okay, come on up here and make sure that I email it to the right place. So it's the Fernandez. All right, perfect. Thank you. Whoops. Okay, you should have it by now.
Oh, thank you.
Are we good there? All right, so 70% of your grade is Zybooks. That means, reading through it, but you're not graded on the reading, obviously. You're graded on two kinds of assignments that he will assign from that book. Some of them, I think they're called challenges, some are called something else, but basically program, small little bits of program. And for some of you, you're just starting out with Python. Python is the easiest programming language to use, I think. And whenever you have trouble, you can come to office hours, which are right after this class for an hour. My office is on the syllabus. It's 025 in Bollier. So downstairs and down the hall. Make sense? Okay, now the other two parts that you're graded on, of course, are class participation, which means you gotta raise your hand sometimes and offer things that you want to talk about, or your answers, or your questions. Answers to my questions, for instance. Then the other part is the semester-long project. And the semester-long project involves you choosing some data that's interesting to you. Maybe it's the music you played on Spotify over the last year. That's what a lot of students did last semester. Or it's you're storing your heartbeat on your Apple Watch. Or it's just some big data set you're interested out there on the internet. Maybe plane flights, or where shipping container boats are. Who knows what, or volcanic data, who knows? Something that you find interesting, because you will be talking about it at the end of the semester. And if you look at the syllabus, there are several milestones. So if you go look at the second document linked on the syllabus called the semester-long project, there are milestones. Okay. Okay, you look at the timeline section. Right now, what you should be doing is just thinking, brainstorming. If you want to work with someone, you can work with one other person. If it's going to be more than that, it's got to be an amazingly difficult project. So best to just work on your own or with a partner. You got to choose a data set by February 2nd. So that's the first point. And this data set, it could be a bunch of images, it could be CSV files, it could be Excel files, it could be JSON, it could be all kinds of things. But by February 2nd, choose the data set, and I'm going to ask you about it in class. You're actually going to write it down on a piece of paper. I've chosen, X, Y, or Z. If something weird happens later and you absolutely have to change it, we can talk about that, but let's try not to. Okay, next one. March 7th, March 9th. These are two different classes. And we're going to do this over two classes in that week. Each of you is going to present a quick demo on your progress. Basically, this is the data set. This is how I'm storing it. Maybe this is how I'm cleaning it. So we just call that demo 1. Next one, April 4th and 6th. Again, 2 days in that week, and just be demo 2. And what I expect is that you will stand up in front of the class. You have your laptop with you. If you want to plug in, you can, but you don't have to. And talk about how much progress you've made so far. Show some data on your screen, and 5 minutes total. Maybe even 2-3 minutes, and then a minute for questions. Sound good so far?
It was February 2nd.
What's that?
It's February 2nd.
February 2nd is you have to choose your data set by then. And on that day, you're going to write down what your data set is. That means you will have already downloaded and looked at it and checked and confirmed this is actually a good data set to use. And number 1, you have to be interested in it. It has to be some topic of interest to you. And then the semester one project final, May 9th and 11th. And you will be randomly split up into these 2 days when the time comes. So this is just a start out, this is the practice, and the demo 3 is just your final demo. Now, in a best case scenario, you have data, you have understood what all the fields are in your data, you cleaned it, you presented some visuals that show you understand the data, maybe you analyzed it, done statistics on it, and even better, you built some kind of machine learning model on it. You've used a package from maybe scikit-learn to build a model of it. Maybe there's one variable you're trying to predict. You're able to predict that variable based on the others. Does that sound exciting? All right. Any questions before we move on?
So like what kind of projects that like the data set you have?
One example is it could be all the Spotify songs you listened to last year. Or it could be your heart rate data from your Apple Watch if you have one, or a Fitbit. Or it could be a movie data set that you found online.
So just like as long as there's like a lot of actual data, everything.
Yes, but it has to be something you're interested in because you're going to talk about it. So one thing you could predict is, given your songs you listen to in 1 month, what will you listen to in the next month? That's one idea. Another idea is, let's say if it's your heart rate, if you were to track other things with your heart rate, like what you were doing those days, and you say, when I do this activity, my heart rate will be this or that. Or this time of day, my heart rate will be this or that. Or given if I got a good night of sleep or not, then my average heart rate through the day is a certain thing. Another thing people track is heart rate variability. Who's heard of that? Heart rate variability. Do you think it's good to have high variability, or is it bad to have high variability? Who thinks it's good? Raise your hand. Who thinks it's bad? Raise your hand. It's actually good to have high heart rate variability. And what it means is that when you're exercising hard, your heart rate goes up, and when you're resting, it goes right back down nice and fast. Whereas if you're not in shape, then it'll probably stay up and it'll be struggling for a while. Other ideas. Let's say you downloaded a big data set about some topic that you're interested in, and I want to see some hands. What are some topics you're interested in?
Soccer,
Soccer. What else?
baseball,
Baseball. What else? Basketball. Okay, so we got sports. So for any sport data set, there's a lot of things you can predict. And the most important one would be who's going to win a certain game, right? If you can predict that right, then you might as well just move to Vegas. You don't need to study anymore, which means it's really hard. What do you think the variables are in predicting whether or not some team is going to win?
their opponent,
Their opponent, yes.
stadium, and weather,
Who is stadium and the weather?
players,
The players.
time of day.
Time of day. How about, let's say you have players that are coming from very far away. They're playing at a time of day when they're normally sleeping. Like, let's say they just showed up to the World Cup or some other event. That's going to factor in a lot. For the players, what are the features you want to know?
No, activity level.
Well, if they've been on the injured roster recently, age, right?
Last.
Yes. Now, can you, for instance, get performance like, how fast they can run the 100-yard dash, for instance, or how much weight they can press? I mean, that may not be important for soccer, but it is important for baseball sometimes. What else can you get on players?
Endurance.
Endurance, yes.
What year their salary there?
Ooh, that's big, yeah. If they're near the end of their contract, they really want to prove themselves.
Their age.
Yep, their age. Whether or not they're named Tom Brady. If they're named Tom Brady, they're probably gonna win, right?
Not this year.
Not this year, exactly. So for most of his career. Yep, higher weight and body mass index, but it's complex. If someone is a lineman in the NFL, you want them to have a really bad body mass index, right? You want them to have lots of fat and weight to hold the other guys back. So all those things can be used to predict how well a team is going to do. Maybe you don't want to predict one game. Maybe you want to predict how they're going to do for the whole season. But the first part of this is just gathering the data and getting into a format that you can visualize. And in Google Colab, which is where you can do a lot of this work, and that's where I want you to do this work, there are a lot of visualization packages. Now, we're going to start playing with Google Colab today. So everybody get out your laptops. I'm going to log in. You're going to want to open Google Drive. That's a good way to start. Then you'll always have it in the right place. That means you have to log into your Google account. All right, has everyone logged into the Google Drive? You're going to want to choose a folder where this notebook is going to go. Now, a notebook is a way to write Python and have it executed for you. Now, it's running on a server run by Google that's free, which is kind of amazing that they do this. Okay, once you've chosen the folder or made the folder where you want this file to be, it's going to be eventually an IPYNB file. But what you're gonna do is you're gonna right click, go to more, and you see Google Collaboratory right there. And you click on that and it'll make a file like that one. Good. Okay. Now, when you create it, you will see something like this. And you can change the name of it by just clicking up here and changing the name. It probably just called it untitled and it was blank. I added one simple little thing of code in here. Let's find out. Can you read that?
Yeah, thank you.
All right. This is just a little starter here. Why don't you guys all put that in? And then, so to make the second line, you press return and it will indent it 2 spaces. You can also, if you want, indent 4 spaces instead, but you have to do that every time. 2 spaces is the default for Google. The way things work in Python is whenever you make a loop or a function or something that has some sort of scope, you're going to indent everything inside of that. So here, we're doing a for loop, but it's got a tiny bit of complication. We'll talk about what each part means in a minute.
Make it a little bit bigger.
I will try.
Okay. So it's just
So that one is running on my computer or their computer?
No, it actually runs on Google.
Oh, so-
Yeah, that's the back end, the Google Compute Engine backend. Google Compute is running this for you.
Are you subscribe?
No, it's free.
Subscribe.
You can subscribe if you want and get more power. It is not necessary for this class. Raise your hands if you want more time. All right, let's jump in. So when you press the little triangle play button here, do you get this output? Everybody raise your hand if you don't. You ready to come look at it?
Oh, yeah. So, yeah. You're expecting spaces or some kind of indication of extensions. So we have to do this. Yeah, I was just.
I don't know if anyone ever say that.
I enjoy it, like, I like reading about it.
Okay,
Exactly.
who thinks they know what range does?
Goes 0 to 9, it's 10.
Yeah. So range of 10 maybe gives us 10 of something, right? Range takes a number, just an integer. And so range of X will give you a list or something called an iterable. You can iterate and get the next one and the next one and the next one. So kind of like a generator, but let's just think of it right now as a list. And it always starts as 0 by default. So it'll be 0, 1, 2, ... until you get to X minus 1. I don't know why they made that decision, but they did. Range of X gives you 0 up to X minus 1. So if you wanted to actually go to 10, you have to have range 11. Okay, now enumerate. What do you think enumerate does for us? Well, enumerate actually puts a number in front of each one. It gives us the I. So for I comma X in enumerate. Now we're going to make a simpler version of this. What I want you to do is we'll copy this and hit plus code to make a new code block. And we are going to get rid of the enumerate. And you have to get rid of the I as well. And we have to change this statement because there no longer is an I. And we have to change the format part too. So once you have what I've written there, then you press play. And hopefully it's not super slow like this.
In terms of that placeholder, is it just a preference? Or is it?
Which part? You mean the colon?
No,
Yeah, the percent sign.
yeah.
That is not preference. That is specific for formatting.
Oh,
I'll
okay.
show you what it means in a minute.
Yeah, okay.
Oh. All right, everybody ready? Everybody get that output? Now, to understand what enumerate does, we just look up. Enumerate puts a number before each one. Now, it seems like that's probably not super useful since they're the same numbers, right? Well, what if they weren't? Instead of range of 10, I'm going to replace it with an explicit list. Let's pretend this is perhaps a list of things coming from your data. Let's say we have 34, 2, 99. Maybe these are values that were recorded on some day. Maybe it's number of minutes of exercise, or who knows what it is. Okay, now we press play. Now we can see why enumerate is useful. If I were to ask you on the 7th day, what was the number associated with it? You just have to scan down. Go, okay, well, if I'm calling 7th, number 7, or if I'm, because it started at 0, I'm calling it 6, either case, I can get right to the number. Now, you may have something in your code which needs to know which element is it. Is it the first element, the 7th element, or the 17th element? And enumerate is how you do that. So that's range and enumerate. Now, let's talk about formatting when you print out. Everything in double quotes here is what I'm planning to print out. It's a format of it only, though. These are the actual values. And the way you write these statements is you'll have double quotes, you'll have some format stuff, then you'll have a percent sign, and then you'll have the values. So format, percent sign, values. Now the percent sign plays double duty because it doesn't just tell Python to look for a format. Inside the string, you identify different parts of your format. These are the things that are going to go in there. D is for a digit or an integer, really. So this is an integer. An integer is always a whole number. S is for string. So percent sign S means that a string goes here. A string of letters. It can mean numbers as well, but it's alphanumerics and it's treated like letters. F is for floating point. And this is the one that's the most complex. We'll go over it in a second. And floating points are the closest thing we have to real numbers in computer science. Okay, this percent sign D, this is first. And what it's going to do, for the first formatting symbol it finds, it's going to grab the first element of this list. Or actually, I put curly braces on so it makes it a tuple. Have you ever heard of a tuple? Spelled like this. Tuple. Like multiple, that kind of thing. A tuple is just a list that you can't change. So if you make X equal to a tuple, you can't switch out the first element with something else later. So this over here is a list of things we are going to print in our formatted statements. It can be a list or a tuple. It doesn't matter. This is a tuple because it's curved braces. If it were square, it would be a list. Here they act the same. So let's see what happens. This first thing in here is a 7. just the digit 7, it's an integer. And here we see the first formatting artifact, it's expecting an integer. So all good, it's gonna work. Now, this one is expecting a string. And the second thing here is expecting a string. Good, it's gonna work. Now this one is expecting a float. And this is a floating point. And it will work. So what I want you guys all to do now is create a new section, new code block. They're called cells. Each of these is a cell. We're going to create a new cell, and we're going to create this string. And you can do it exactly like I did it, or you can change the letters or numbers if you want over there.
Sorry, I was trying to keep up with this. I just missed, when you said 0.3 float, or were you specifying how many decimal places?
Exactly. I didn't say it,
Oh,
but you guessed correctly. That when you put a 0.3 in between the percent sign and the letter F, that indicates we are going for 3 significant digits here, or 3 after the decimal point, really. That's why, even though I gave it 7.012356, it only included the first 3. Did everybody get the same output? Anybody one more time? All right. So what we see here is we didn't even print the string, but it told us the value. And that was just a nice thing for it to do. The Python interpreter converted these 3 values into the same string. Now remember, a string is a certain kind of object in computer science. Even though we see this as like the number 7, it says 7.012, the computer will think of this object as simply a list of letters and numbers. They're just letters in a sense. Like the way you think about letters is the way it's thinking about these things. And it can put them in Python in between single quotes or double quotes. Now, sometimes when I'm quoting something that has an apostrophe in it, I definitely use double quotes. If I'm quoting something that has a quotation in it, then I might use single quotes because I want to put double quotes inside the string. So I've given you a couple little things to play with. What I encourage you to do is go home and practice on some simple Python tutorials. Grab some Python code that looks interesting. Throw it in here. Change it. See what happens. And then we will open up the laptop a little bit every class, almost every class. And we will have some time to learn one little thing. So come ready with questions. Any questions right now before we jump back into something else?
What are the percentages used for?
Okay, so if it's inside the string, percent sign means right here, I'm bringing in a variable from outside and I'm gonna format it a certain way. So right here, this one means I'm gonna bring in something and it better be an integer. Because it says percent D. This is string, this one float. Right here, after the double quote on the outside, since you have a percent sign there, that one's indicating to Python, you better format this string. We'll look for formatting symbols inside. And it's kind of the glue between this part and this part. Okay, last time we left off here. The data in the world. And there's a lot of it. And these are zettabytes. And every zettabyte is a billion terabytes. Yeah. And just look how fast it's going up. Right now, 2023, this year, we're probably going to make 120 zettabytes worldwide. Just to give you an idea, let's just choose photos, for instance. The digital camera was invented in the late 1970s. Does anybody know by who? No? Ever heard of Kodak? Have you all seen Kodak around lately?
And then you get bankrupt.
What?
And then you get bankrupt.
They went bankrupt. Why did they go bankrupt? They depended on paper film for their business. Selling it, developing it, developing prints for you from the film. It was like $7, $8 to buy a raw, unexposed film case, and then another $7, $8, $9 to develop it afterwards. So you're spending, $15, $16 just to take 24 pictures. So you don't take that many pictures, right? Well, later on, when we were looking at through the 80s, the development of the digital camera, executives at Kodak looked at it, oh, it sucks. A year later, oh, it still sucks, it still sucks, it still sucks. But then eventually, it was as good as the normal analog cameras. And they figured it'll probably compete for a little while, but no, it got doubly better every year, doubly cheaper every year. And just went on this, exponential curve until by like 2012, we're talking 10 years ago, probably by 2012, the world was taking more photos just on their phones than had been taken in all the time on paper film. So if you took all the Kodak and Polaroid pictures from the past that all humanity had taken in all time, it was less than the number of pictures we take in 1 month on our phones collectively as the world. And that was in 2012, so you can imagine now. And if you count separately every image that comes out in one of those burst pictures or in a video, I mean, does anyone have any idea how much there is on YouTube right now in terms of hours or years? What's it? It could be, I don't know, but I know it's
longer than the history of the world.
maybe. That'd be 4 billion years, it might.
Sorry, human existence.
Yeah, the human existence, that'd be depending on how you define humans, right? Supposedly like 60 hours are uploaded every second. I mean, you can't keep up. There was a time in history when you could keep up with all the TV. They'll come out with new shows in maybe the fall, early fall. You could watch that show. It'd have 22 or so, maybe 24 episodes. It was based on the marketing cycle for automobiles. That's how show season started. We have seasons of shows because of automobiles. They can only make new automobiles every year. So
the advertising from automobiles was like the biggest deal, and TV was structured around that. So there was a time when you could have watched all of TV that existed to keep up. But you can't do that anymore. And you probably couldn't do that by the time cable started. Once we had 100 channels coming into your home, then it became too much. Can any of you guess when was the last time in human history when you could have a professor that teaches all the subjects at a university?
Like 200 years ago.
Something like that. I heard it was Leibniz, who was a co-discoverer of calculus, and I think this is the 1700s. He could teach all the classes at his university. And after then, you have to specialize. Nowadays, if you're a doctor, you can't just be a doctor, you have to specialize in something. If you're a practitioner of anything, you almost always have to specialize. Even if you're a YouTuber, you can't be general and talk about anything. Everyone has their own little tiny niche. But yeah, there's a lot of data in the world. Okay. Here we have two ways of thinking about how to handle data. The old way at the top and the newer way at the bottom. Now, both of these have some kind of machine learning involved that are represented by this. That's just a picture of a neural network. But it could, in this example, just represent any classifier, any kind of machine learning system that's making a decision for you. In the old way, you would always have a human who's looking at the data and figuring out what are the important features. For instance, if we have pictures, let's say we have a photograph and we're trying to decide if it's a dog or a cat, and I can't even tell, and I drew it. So if we're trying to decide what animal this is, then the important features are decided by a human in the old days. And you would do things like defining the features in terms of, width of different parts and length of different parts and where they are. Like if you can find the head, then you look for something a little bit behind and up here, and that's the ear. Or alternatively, maybe you have an ear that's a floppy ear, it goes down here. You have the paws, and you can look for, are there visible claws or nails? What kind of mouth is there? Is there a tongue hanging out? What kind of tail? Deciding what the features are, whether they're big coarse things or tiny things, like maybe how fuzzy is the fur. A human in the loop deciding those features is called feature engineering. And it's something we used to do a lot. Largely, it's gone away. And the reason is because we now let machine learning do not just the classification, but the feature learning as well. It learns the features on its own, which means we don't have it to give it any information on where things are. We literally just hand it the whole image. And then it looks at the image pixel by pixel by pixel by pixel. And it learns everything end to end. So this, we would call this bottom one an end-to-end system. The machine learning is doing everything from the beginning
and all the way to the other end. Seems easier, right? Seems better. What could go wrong?
The machine learning, based on its data set, could lock on features that aren't actually relevant.
Yes, exactly. What were you gonna say? Let's look at my favorite example. What were you gonna say?
With the backgrounds to the.
Yes. Did I talk about that last time? Or, okay, that's what happened.
There was that one project in the wolves, dogs, whether it's.
Yes. Exactly. Were you gonna bring that up too?
No, I was gonna say, just memorize this stuff. It's actually learn.
Ooh, if you memorize instead of learning. Well, that's all it's doing anyway. In a sense. Yeah, and we'll get deeper into that later, but there are people who now believe, who I respect, that deep neural networks, including ChatGPT, which you may have played with, all they're doing is they're creating massive lookup tables. Really complex lookup tables, but lookup tables nonetheless. You could think of them as branching lookup tables. We won't get too deep into that math. Okay. The example he brought up was they had a husky wolf detector, husky versus wolf. Did I mention this last time? No? Okay, they had huskies and wolves and they looked very similar. And they would have some picture of a wolf. And it's a picture of a wolf. And they were classifying these like 99 point something % accuracy. Woohoo, we're doing great. And then they secondarily had another model that probes the first model to figure out what it's looking at. And they ask it, which of the pixels in the image are most important to your classification? And when they asked it that, it was looking at the snow behind the wolf, because all the images they had of wolves were taken outside in the winter. And the pictures they had of huskies were taken by their owners, either inside or in their yards in summer. If a network can learn from something easy like this, it will. Another famous example, they had a bunch of images of cancer. So they had images of tumors. And some of these scans had tumors, some did not. Some were just healthy people. So let's say they have some scan, okay? And there's just whatever, body parts in here. And then there's this one tumor, and it's right there. And in order to give context, they always put a virtual ruler in here so you can get an idea of how big the tumor is. And maybe it'd be off in the corner like this, and it'd have some markings. And that way the radiologist could see how big the tumor is. Well, they trained a perfectly accurate model, an AI model that could tell whenever there was a tumor present or not. And then they asked it what it was paying attention to. It was this. Whenever the ruler's there, it must be a tumor. If these models can cheat to get to a good answer easily, they do. And it's because of the way they learn. Let's say that you learn with just being in the right place in this room. Let's say that there's only 2 parameters for your model. There's this way and there's this way. So right here, let's say with this parameter setting, I get to maybe 50% accuracy. But over here, I get 63% accuracy. And over here, I get 89% accuracy. And then this spot right here, I get 96.3% accuracy. And then here it goes down to 92. And here it goes down to 80. What this room becomes
is a landscape that goes up to here, or you can think of it as going down if you're calculating the error. So right here, I make a few errors, or the error amount is the least. So if I started with random settings, let's say I started here, I'm just going to go downhill, right? Like rolling a ball. Roll the ball downhill. And then eventually it gets to here. If one of these two dimensions happens to be representing pixels in the background, I don't care, I'm a computer. I don't know what anything means. I just go where gravity sends me. So that's one of the dangers of letting the computer decide what the features are and how important they are. But it still saves a lot of time. All right, here is an example of taking data just like the what I was talking about. This looks like maybe not cancer, but these are definitely slides taken of samples in the lab. Tumors and normal. So typically what you do is you have training data that you know what it is. And in this case, we've got two sets of images. We got ones with tumor and ones that are normal. And when you're training it, you basically throw it in some deep learning model, and up the output, top right, probability of tumor. When you're passing through one of those tumor pictures, and then let it say that probably tumor, it predicts, 0.2. Well, that's wrong. You want to push it toward 1, toward a 1, 0. And the way you do that is you tell it how wrong it is. In this case, if it predicted 0.2, but you want it to give a 1, then you tell it you were wrong by 0.8. That is it's known as the loss, also known as the cost. We use a lot of words to describe it, or error. And then what that does, when you tell it not only that it's wrong, but how wrong it is, it can use that to adjust everything inside of where it says deep model. And it adjusts all those numbers. And then the next time you give it the same picture, it gives you a number a lot closer to 1. Now, it may not be perfect yet. You may have to train it many, many times on the same data. When you train it on all your data once, that's called an epoch. And for a lot of models, we do 100 epochs. Maybe. We go through the entire data set many, many times. Now, GPT is an outlier. They don't. For GPT, they trained it on their epoch, on 1 epoch, but it was a really big epoch. They took 1.1 million years worth of English text, assuming a rate of about 20,000 words a day. It was over a million years of English, and they exposed it to that, but they did it once, but it cost millions of dollars. Okay, so in your test set, you need to also have positive and negative examples. And what you're going to do, you're going to give it a bunch of examples with a tumor, see how it does, examples without a tumor, see how it does. Does that make sense? If you had, let's say, 10,000 images in your training data set, is it important to have 5,000 of each for the normal and the tumor, or can you have just a few of the tumor and a whole lot of normals? What do you think? Even distribution is best.
but it's not always possible. Let's say you're doing fraud detection. There could be, 10 billion transactions today on credit cards across America, but less than 0.0001% of them are fraudulent. So what do you do then? What's going to happen?
Give it examples that you know are flawed and start trickling slowly.
So the ones that you have that you know are fraud, make sure you focus on them or bring them in more often, right? That's one good way to do it.
Can you try and force that 50-50 ratio?
Yes, you can do that by either throwing away most of the normal examples, or you can create virtual epochs where you're not going through all your data, but you're going through all your negative examples and some random selection of the positives, or vice versa as needed. Now, if you don't do that, here's the danger. Let's say you build your fraud detector, right? And let's say we have, these are all the transactions. And let's say inside there, there's that ratio of them are fraud. That's the fraud. You can think about that as 0.01%. Okay. Now let's say you train your predictor and then you go to your boss at whatever company you're working at and you say, I've got great news. My predictor is 99% accurate. Yeah. I mean, you can get 99% accuracy by this program right here. There, I made a 99% accurate predictor. It just says not fraud every time for everybody. So yeah, the only way you know if your model is doing anything intelligent at all is if you can do better than what this does. That's why, yes, it's important to have a balanced data set if you can, or to analyze it with this in mind. What is that? Who knows? CAPTCHA. Yes. And what is it meant to do?
Stop robots or programs from getting on the site repeatedly, buying a product or something of that sort.
Yep. Yeah, so a guy at Carnegie Mellon named Louis von Ahn, if that's how you spell it. He came up with this idea. He was brainstorming ways to come up with things that are hard for computers, but super easy for humans. Yeah, so they had to make other ones, and we'll talk about that one next. But for a while, this was really hard for computers. And the only reason we had these out there was because they were hard for computers, but they were easy to generate for a computer. So a computer can select random words and then have random functions to mess those words up in some way. Either contort them, twist them, make them different colors, put a line or a shape in front of them, and your visual system, which is like your own personal deep neural network, can unwrap that and deconfuse it very easily. Only way to be sure. But for a while, Before deep learning was a big thing, deep neural networks couldn't do that. So they had to replace with something that was even harder for a computer, which gives us this. What? Why is that harder? How many of you guys have seen this recently? It's all over the place now.
Wouldn't the computer like be noticeably robotic the way it moves the mouse?
Yes. Someone over here gonna say that? No? But yes, that's right. What does that mean to be robotic in the way it moves the mouse?
It would click the box way too fast.
Yeah. Yep, so maybe it's speed, but then you could put a random pause.
Probably like the very center.
Maybe in the very center.
Isn't that like a instantaneous teleport to the box instead of an actual slide?
It could be that as well.
Probably take a straight line path to get there.
Yes. Humans have micro movements, jitters. Our muscles don't do anything the same perfectly for any amount of time at all. If you look at your finger under a microscope, even if you hold it perfectly still, it's vibrating. And that's because when you hold your hand still, the muscles that control your arm are not just staying on. Your muscle cells are tightening and loosening, and they're taking turns. So it's different muscle cells that are turning on and off at all times to make your hand not move or to make it move smoothly. So as you move smoothly up to this box and click somewhere in it, that path has a lot of imperfections in it. And there are ways we can understand something like this. There are mathematical ways to characterize that roughness. That's how that works. Last question.
What about like on phones when you're just tapping phones instead of actually like scrolling, dragging the mouse?
Yes. In fact, there's a company out there that has a system where they can recognize who you are based on those little movements. All right, guys, I will see you in 2 days.